time for us to get with the calculus, okay? With the calculus, the first thing I need to do is teach you some background information so that we can go forward. Here's the background stuff. As we did before, in any case, if I have, that says, this is the antiderivative of dx, where dx is an infinitesimally small x, delta x. And when you take the summation of that, when you add them all up, you get delta x, which is equal to final minus initial. And if I wanted to know exactly how much it is, then I put on limits. I put in my final minus my initial, and that gives me my delta x. Now, this does not have to be just x. This could be a function. If it's a function, you do your antiderivative where x is the only variable, and then you take the final function minus the initial function, and you get your answer. In all cases of what we're going to do with gravity, you are going to be looking for a delta something, a differential. And if you have that differential and you add them all up, you get the final. For instance, as we did last time, du ends up being delta u, and if your initial is 0, it ends up being u. In this class, we're also going to be doing this. Our small amount of gravitational field will end up giving you your gravitational field, etc. Now, what goes in here can get more complex. In electricity and magnetism, we did one called Biot-Savart, and this little equation was terrible. It was very, very complex. However, once you trust, again, once you trust in the process, once you have this to be true, and you identify your differential, you do the calculus, which may or may not be complicated. And that's where you get help, and in some cases, we're going to find out very, very quickly. We have one that we can't do. I mean, I'm sure the third-year calculus kids could, but in the book, it literally says, which is found in a calculus textbook to be this. And you're not expected to do it, because the calculus is too hard. But if you can set it all up, you've done the physics. The calculus can be done by the mathematicians or in a book or something like that, but that's beyond the purview of what we're going to deal with. So, one of the other things that we found out in our introduction, when we talked about the potential energy of the bar that was at an angle, we ran into an issue where we wanted to add up all of these dm's over a distance. Here we're going to do the same thing. In this chapter, we're going to have a bunch of little dm's. We're going to want to add them up. The problem is dm cannot be added up as x dm, x2 dm, x3 dm. We're going to have to change a mass into a distance. And that's where we get these fine things. They're called mass densities. They can also be working as charge densities. This one is defined as, this is lambda. Lambda is defined as kilograms per meter, which could equal your total mass divided by your total length. It's a line density. When would you use this? When you're dealing with something you're adding up in a straight line. If I make these infinitesimally small, it also equals dm over dl. And as we know in physics, if they have the same units, in a lot of cases they're the same. dl might be dr, might be dx, might be d something with the units of meters. Then, what if we're going to add up areas? If we add up areas, we'll use area densities. And our area density is sigma. And that, of course, is defined as kilograms per meter squared, which will be your total mass divided by your total area, or your small infinitesimal mass divided by an infinitesimally small area. You might say, how could you have an infinitesimally small area? Well, if I were to have a piece of paper and I were to slice it up into little strips, you might say, why would you do that? It's possible, and we actually ran into this in electricity and magnetism, where we had a non-parallel plate capacitor, and as it was moving up, each one has a different quantity, but in the lengthwise, it's equal. Okay? And then, of course, this gives us our volume density. And our volume density is rho, which is the same density. For instance, if you wanted to find the density of steel or copper or something like that, it is defined as kilograms per meters cubed, which would be your total mass divided by your total volume, or dm divided by dv. And that's one you'd have to be careful with. A lot of times when I'm writing this one, I will do it this way. I will very often write, instead of writing a big V, I'll write volume. It takes 2 extra steps, but would you agree if you do that, you're not going to run into the problem of saying, oh my gosh, I have a velocity. No, volume. Or in electricity and magnetism, you might see that and say it was voltage, which again would put you in a bad spot. Well, let's do a very simple example of how to use one of these. We're going to use these in a lot of the different derivations of gravity coming up, but let me just show you one simple one. If I were, again, to have an object, and let's just say that this is mass m and a length L, and I needed to say, I'm at a point right here, point P, and I want to say this is at 0, this is at L, and I want to find the gravity due to this bar. Well, a little m right there would have a particular gravity, gravitational field, but this one would have less, would have less, would have less, because r is continually increasing. So what I would do is, let's just call this, we'll call this x naught. Well, actually, we just call this 0. That would be even easier. And let's just take a very small dm. And that dm would have a distance from P of r. Well, r would equal x naught, and if we call this x plus x, or we could call this, whatever we define it. But when you put this into the equation, you can't say, well, dm1 plus dm2 plus dm3, they're all equal. But I can do this. Because it's a line, I'm going to use my line density. And I'm going to say that my line density is defined as the total mass of the bar divided by the length of the bar, which would also equal a very small, infinitesimally small piece of the bar divided by dx or dl. Because if the object is uniform, if you have a uniform object, then a small piece of it has the same density as a large piece of it. And then it's simple enough to say, oh, well, dm equals lambda dx. This is now a constant, which can come out of an integral, and the dx we can actually integrate.